Today we're gonna talk about Hahn spin echo, and this is a technique originally developed in the field of MMR, and is um, it is also employed in the field of quantum information processing. Okay, and so let me first explain what the problem is, and so that we know what's the need, why there's a need for this technique. All right, so I'm just gonna use our experimental setup to explain why this is needed. Okay, so we have this diamond, right? So it's basically a cube, a very small cube. There are many MV. Okay, don't mistake don't mistake this as spin. This I'm using this to represent the molecular axis, the molecular axis of the MV center. Uh, Let me remind you again that in this experiment, we do not manipulate the spin individually. What we manipulate is the molecular state of the new MV center. Yeah, in NMR, we we use the field, either the static field or the uh, the microwave field to manipulate the nuclear spin, which is it's embedded. It's the nuclear spin of say water. It's represented by this. So I'm just gonna use it and hollowed arrow to represent the spin, and this arrow represent an exit. Okay. Here in this case in NMR, we manipulate the spin, like we literally manipulate the spin as a tiny magnet, right? We make it move this way, that way, and it process in the field, right? So it does all kind of things. We manipulate its spatial orientation, right? But in this case, we don't, because this is a 2-electron state. Remember, what we're manipulating is transition between m equal to 1 and m equal to 0 and m equal to -1 or +1. And in this case, it has an orbital. So the wave function, the quantum mechanical function, has an orbital part, which depends on the position, right? So it's just like atomic orbitals, and it has the spin part, and that spin has, in this case, that spin has a 0 value, so it is zero, no spin actually, and in this case, it has a net spin. Okay, spin equal to 1. Okay, orbital. So we are controlling quantum mechanical transition between these two states, these two quantum states, not the physical orientation of the electron spin. Yeah. Okay, I want you to remember that, because I feel like that's an impression that many people has, since we call this optically detected magnetic resonance. So a lot of people just equal that to, so this is ODMR, right? So since this is the same, a lot of people just equal this to that. It is not. All right, so we'll come back to this. Actually, you know what? It wouldn't be harmful if I also have a parallel example of NMR by my side. Okay, MMR. This is MV qubit. Okay, so yeah, since this technique was originally developed through MMR. Okay, so B1, 1, 1. Okay, so we know that the Zeeman splitting, of course, there is a splitting between these two states because of this spin-spin interaction in here, right? Otherwise, it will be degenerate with. So it's probably even more accurate if we just draw this. So this state the same. So this is the degenerate state, and this splitting is due to spin-spin interaction. let me just use 1 plus 1, spin interaction. So here we have this, and these two electron spins interact with each other. Okay, and when we so this could already be a qubit, right? Except that this is degenerate because you have plus and minus 1 both here, and so if you apply a microwave pulse, this will move population from n equal to 0 to both n equal to plus 1 and minus 1, and that wouldn't be good because then you have a 3-level system instead of a 2-level system, and a lot of protocols that we develop for quantum information processing cannot be applied. Therefore, we typically would just add a field, a B field, a static B field to lift off this degeneracy, and for n equal to plus 1, it is here, so it goes up, and minus 1 goes down. Now, the amount of splitting, or the amount of splitting here depends on the B field, right? Some of you have written report for lab 1B, knows this formula. Therefore, different spins have splitting according to its local magnetic field. And since our static field was practically in the experiment, the static field is generated through the coils. It could have spatial inhomogeneity. That means, for example, if your coil is like this, right? Even though, although your MV is very small, it could still have a gradient across it, right? It could still have a gradient across it. So MV here could experience an MV, experience a little different field than the MV here. If we've called this B0, B naught, this will be B naught plus some delta B, okay? And the same goes here. In the MMR, we usually have liquids, okay? And liquids is typically contained in like a 1 millimeter or few millimeter container. So there you have even bigger. So this is like the liquid for whatever solution you use, and again, in the same way, if this is B0, the nuclear spin that is far from it will experience a spatial. There is a spatial dependence of the static field. Thus, you will experience a different local magnetic field. Yeah. Okay. Why this is a problem for us? Because the resonance depends on the local field of the MV center, right? Therefore, you have an ensemble of qubits with a spread of resonance frequency. Okay. So MV1, let me just call it MV1, MV2, and this is at different positions. Okay. MV1, MV2, MV3, they all are in different locations. So here, if this field is, the resonance frequency is omega naught, this could be omega plus some offset. It's okay. It could be like this. Okay. Or better yet, let me just redraw this. MV1, MV2, MV3. This is omega naught, this is omega plus, and this is omega minus. Something like that. Okay? All right. So why this could be a problem? Because so the signal that we use to probe the population in the graph in the states is the fluorescence, right? It's the red light fluorescence or center around 660. Okay, so we get signal from here to here to here. Yeah. So when we collect the signal, it is an incoherent sun. It's basically an incoherent sun. The signal that we collect represent 1, 2. Okay, let me just say 1. 1, 2, 3. Okay, the signal that we collect is from different MV center, and they are just an incoherent sun. Why do I call it incoherent sun? Because each I is proportional to PIE, right? Population in the excited state. By excited state, I mean the n equal to +1 or -1 state. Okay, so it's from different MV centers. Okay, so therefore, if we try to say of PE from different MV center, so if we try to measure the, say, if we try to measure a resonance spectrum, which you have all done, right? So say this is a Rabi spectrum because I use one pulse and that's a Rabi pulse. If I do this, then what happens is this center will be shifted for different MV. So this is MV1, and the other one will be MV2. And this is this offset. Got it? Okay. So you have a little broadening so the incoherent sun, the result of the incoherent sun is that you will have a slightly broadened Rabi spectrum. No big deal. I mean, it is limited by the pulse width anyway and power broadening anyway. So no big deal. However, if you're trying to do coherent manipulations, then there's a big deal. Okay, what I mean by that, remember Ramsey pulses, right? So this is one pulse, and this is pi. If I have two pulses, pi over 2, pi over 2, that's a Ramsey pulse, right? Do you remember that the spectrum is supposed to look like this? With fringes on it? This is a result of quantum interference? Yes? Everybody following? Do you still remember? All right. Let me just say, the reason for using 2 instead of 1 is because you want to narrow, you want to overcome your limit of the pulse, the transient pulse width, the transient broadening. So yeah, it's called the transient broadening. So on top of the power broadening, you also have the transient broadening, which is associated with the pulse length. Okay, it's just a Fourier transform relation. In order to make this narrow and narrower, so that we can pin down the central frequency, you want to use a long Rabi pulse, right? But like I said last time, it's really hard to keep, the phase stable for such a long period, and then and this and that. So there are many reasons, technical difficulties that there exist many technical difficulties for us to use a really long Rabi pulse. So instead of a long Rabi pulse, we use 2 short pulses that are separated by the length of the long Rabi pulse. Okay, but this still need to be phase correlated. Anyway, as a result of this, because your ground state could be excited here or could be excited here, there are two different excitation paths and they interfere, blah, blah, blah. So you have quantum fringes. Very nice. And this is narrow. This is as narrow. This is proportional. The width of this is proportional to 1 over tau. So this is tau, and this is like 1 over tau. So the longer you separate them, the narrower it is. And it's easier for you to pin down like the central frequency. Yep, good. Now, so this is your first example of coherent manipulation, coherent control of MV center, right? Now this is for one MV. For the next MV, for MV here, you will still have you will have the same Rabi spectrum, but you have the same Ramsey spectrum, but slightly shifted. Yeah, by this amount. So this is MV2. I'm sorry, this is, I use the wrong label. This is MV1, this is MV2. It's slightly shifted, okay? Now, because this width is so narrow that this shift matters a lot. What the outcome of this is, so the outcome of this is that the dip will align, could align with the peak, the dip align with the peak. Therefore, you have no, you lose your frequency resolution because this is what you get experimentally, right? You get an incoherent sum of signals. Okay. So this is what you get experimentally. So that's bad. Yeah. And there are also other things. This spectroscopy is one thing. In a quantum circuit, you have many gates, right? Many operations, one after the other. Yeah. And all of them are coherent manipulations. They all deal with superpositions. Okay, so they do something like this. Okay, so the outcome, so you have MV1, and this is the outcome of MV1. And you have MV2, and this is the outcome of MV2. And they are the same, mostly, but they have some slight displacement somehow, okay, depending on your application. And when you have an incoherent sum of them, it kind of wash out the feature you're looking for. It typically wash out the quantum feature you're looking for, okay? So this systematic, error, we call it dephasing. Okay, so this is, individually they are fine. They are quantum mechanical, they have good coherence, and that's all good. But when you sum them, because of this technical imperfection, it produces a systematic error, and that kind of wash out your whatever quantum feature that you're interested in. And this effect is very much like decoherence, except that this is not decoherence. Decoherence concerns the loss of coherence. So U and V, remember when we talk about block sphere, we have the density matrix, which can be characterized by 3 numbers, block vectors. This is population. These two are the real and imaginary part of the coherence, right? If you have decoherence, the magnitude of this will drop, okay? But if you have dephasing, nothing happened to these numbers at the single particle level. But because of this shift that we have, when you have an ensemble sum, which is an incoherent sum, so incoherent sum is usually just, this is ensemble effect. When you have an ensemble sum, then that fringe washed away because it's displaced, simply because of displacement. Okay, we call this dephasing. but you can understand it physically as some kind of displacement of quantum signal. Okay, we call it dephasing. And this, since it is not fundamental, it can be fixed. All right, there's a way to counteract this imperfection, and it's called the Hahn-Spin echo. Okay, if it is the coherence, there's no remedy. It is cancer. It's deadly. Okay, but if it is dephasing, there could be a way to, there could be a counteract for it. Yep. All right. So how does this work? How does Hahn-Spin echo work? So it was first developed for the field of for experiments in MR. And whatever I talk, like this thing that I talk about, also happened here. Yeah. So, but I'm just gonna explain how it works. I have a feeling that today we can manage finish the lecture within 90 minutes. I think we can do that. All right. And let me just draw again for the Bloch sphere for this example. So this is a Bloch sphere. This is your original state of NV1. Yep. This is your original state of NV2. I'm just going to use 2. It should be sufficient. Okay. X, Y, Z. Okay. Of course, this is not real X, Y, Z. This is the Hilbert space. Okay, this is Bloch sphere, but I'm just going to use X, Y, Z anyway. Okay, now, when we apply over 2 poles, what it does is it will rotate. It kind of follows the right-hand rule if it's on resonance. Anyway, that's beside the point. What it does is it will rotate this to here. Yep. So if this is omega naught, this is omega naught plus some tuning. And if this is unresonant to NV1, then it will put it on the axis of X. But if it is off resonant, which is off resonant with respect to NV2, right? Then you will put it, sorry, I should just draw it here. You put it here. Slightly off the axis. And actually, you know what? I need 3. I need 3 NV to explain how this works. So this is NV3. Okay, for NV3, since it has a different detuning, the opposite sign for that, so you'll go here. Yeah. Notice that these are still kind of very, very close to the equators. It is just slightly different phase. That the phase is off. There's some kind of phase offset from your target Bloch vector. Okay, so there's a slight phase deviation, but they are still on the equator. That means the omega 1 is now 1/2 0. Omega 2 is 0. Omega 3 is 0, right? Because, sorry, now omega W. W is the z coordinate, right? So their z coordinate are the same. They're still on this xy plane. Just they have a little phase deviation. Yeah. Okay. Now, So in this case, you have like a waiting time between the two pulses. So you wait, right? And okay, here's the tricky part. Normally, so I'm gonna explain something called the rotating frame. Just like free precession in NMR, a block, a quantum spin, a block vector, also will, as long as it's not aligned with the or anti-aligned with the z-axis, as long as it has an xy component, uv component, you will do this. You will do this precession at its natural frequency, in the same way as a class, in the same way as a classical spin in MMR. Okay, so they will do this. Okay, and all of them will rotate clockwise. Okay, clockwise. So clockwise means minus, right? Okay, clockwise. They will all rotate clockwise at their natural frequency. Yes? And their natural frequency. So they all run, but run at different speed. Yes? So if you could apply, you can continually apply a rotation transformation, a global rotation transformation to all the vectors at rotation transformation. So what is a rotation transformation? Is this. This is a counterclockwise rotation transformation. So if you have a vector, it gives you, it rotates this vector counterclockwise by an angle of theta. Okay? So that's this. 0, 0, 0, 0, 1. Okay? And this is UVW. All right? So this is counterclockwise. Clockwise. Counter. Counter clockwise. Okay. If you continuously apply a counterclockwise rotation at this angle, which evolved with time, then you can undo the precession. And this is just a mathematical transformation of your representation. Okay, since this is unitary, it's no harm. Yeah, it's no harm. The probability is still 1. All the observables still maintain their original property, so this is no harm. So this is mathematically legal. It does not change the physics. But anyway, you make the representation easier to gain insight. You make it easier to gain insight from here. So if you do this, you can undo this free precession. And this thing, this guy, will look still. Okay, so this is called the rotating frame. You go to a frame, you kind of rotate yourself with it. So you can imagine that these are all kids sitting on the merry-go-round. And if you're standing outside the merry-go-round, you see they're all rotating, right? And if these kids are running on the merry-go-round, you don't know which one. I mean, yeah, you know which one is leading, but it's kind of hard for you to like see it. They all go around, and some run faster, some run slower. But if you stand on the merry-go-round, it is easier for you to see who runs faster, because the motion of the merry-go-round is removed. Yeah? Okay. So I think this is a great example. So I'm going to use this merry-go-round. So yes, excellent. I like that. So I'm going to just go with this color. This is the left frame. Left frame. And they all go like this. Oh, sorry, clockwise. They all go clockwise. Some go faster, some go slower. So this guy go faster. This guy goes slower. Yeah? Good. Now we are by this continuous rotational transformation, which has an angle that depends on t, omega t, we can undo the rotate. We can undo the motion of the merry-go-round, rotating frame, so such that this guy will appear still. And this guy will go like this at the speed of omega w, and the other guy, on the other hand, will go like this, minus omega w. Got it? Okay. So let me just label it. Yep. All right. Good. Why do I want to say that? Because now if we go to the rotating frame, then the evolution, the free evolution of this will become like this. This blue vector will keep aligning with the x. It's that kind of fixed there, pinned to x-axis, and this guy will go like this. Actually, it is not. It is the opposite. I mean, it should go. Oh no, it's fine. Yeah. It is. Anyway, I won't worry about the details. This guy will go one direction, and this guy will go the other direction. Got it? It'll be like a fan that spreads out. Yep. Okay, and this spreading out is a problem when you apply a second pulse, right? Because when you apply a second pulse, this guy is still here. The other guys they all moved away. So the result of this rotation should have been this, right? So if the first pulse is bring you this, the second pulse will bring you further down, right? So the second pulse should bring you here. But since they are moved away, they will not brought here. They'll be brought to other places. So that's a problem that we talk about as called dephasing. How do we fix this problem? We fix this problem by, funny enough, adding more pulses. So if we do, let me just use this. So if we add another pulse in between, called a pi pulse. So these are pi over 2, and this is pi. Then it will bring them back. It bring them back to focus. How does that work? So pi, in general, so from this example, if you apply a pi over 2, you bring it to the equator, right? You bring a pi over 2, you bring it to the south pole, right? In a sense, you're flipping it. So a pi pulse flip your spin. So in the same way, if you apply a pi pulse here, when this is moving away, you apply a pi pulse. What it does, it will flip it to the other side. Okay, if this is a north pole, before you apply the pi poles, this will be the south pole. Okay, and you flip also this to the other side. Okay, so you weight. So if this is tau, you weight tau over 2. Okay, so you don't wait till the end. You wait like midway. You meet it midway. You intercept it, and you flip it at midway, pi over 2, and then you let it free evolve again. Right now, the the this will continue go this way, and this will continue go this way. Yeah. So when you wait for another pi over 2, tau over 2, they'll come back to here. It's like refocusing the light. You have a light that is divergent. Some go to the positive direction, some go to the negative direction. You use a lens, give it a kick, invert it, and they'll come back. Okay. Right. Okay. Let me see. What else do I want to say?
I have one question.
Yeah.
After the experiment, I still don't know what's the significance of tau. Like, if we increase tau, what's the effect on the system?
With which pulse configuration? Ramsey or Ham?
Let's just say Ham.
Okay. Ham? That's a good question. And we will come to that in a minute. Let me first think if I missed anything.
The red line and the green line because they rotate pi about y-axis.
Yeah. I'm thinking about that too. Let me see. Do we invert? Your question is, do we not only invert the position, but we also invert how they rotate?
Rotate about y-axis.
Mm-hmm.
So the red one after a pi pulse will go to the dash green line.
Oh.
And then they will go back to the blue line.
Oh. Is that so? Yes. You are right. Thank you. Yes, I'm sorry. He's right. I'm wrong. Good. Thank you very much. Yes, I made a mistake. I make a mistake. So the mistake was he was pointing out that you don't the pi pulse does not really just flip you to the other side. It is actually a rotation with respect to a certain axis, just like in NMR. For when you have an initial position like this, you're rotating with respect to y, so you do this, right? When you are slightly off, when you are slightly off from this position, when you are still here, then you do another pi pulse, pi over 2 pulse. It will rotate it with respect to y, and it will bring to here. Right? No problem. But when you are like here, what you do is you rotate it with respect to y for it for 180 degree. So you would so you will do so you will so the circle is like this. So you'll come here. You guys,
it's also on the right side of it.
right.
Okay,
It's on this side. Sorry, this is not a great drawing. Let me just draw it again. So you follow this circle, and you come to here. Okay. So it is rotation with y, not just flip it to your mirror position. Okay, so I was wrong. Sorry. Okay, so this is that, and and uh, and this will be this position will be let me just use dash. This position will be this guy, right? All right. Okay, now let's see. This continue to go this way. This continue to go this way. Okay. So they are here. So they will end up here. After this time, after the pi tau over 2, they'll go here. And but then they will be rotated to this position, right? That will be a different position than this. You mean move this to here?
The first pi over 2.
Uh-huh.
Is this also rotate about y?
Yeah.
So it will not.
I mean, so my point is, this guy MV1 will be moved here, but MV2 and 3 will be moved here.
But everyone also flip side of pi.
Oh, sorry. All right, I'm so sorry. I'm so dumb. You guys are smart. Okay, he's right. So this guy, yes, it is standing still in the rotating frame, correct. So after pi poles, it gets to here and it starts rotating, right? But now we are on the rotating frame, so it's standing still. But under the influence of pi, this is also flipped it this way to this side. Okay, okay, that makes sense now. So when you wait for another tau over 2, this will come back to the same position as this guy, of the omega naught guy, of the resonant guy. So they will be together, happy, and then they will all end up in this position. Okay, so this is wrong. They'll all end up in this position. Yeah. I can see you're confused because I can't flip back and forth.
How do you know which way it rotates? Like, I mean, for me right now, this looks like Chinese.
Yes, I understand. Chinese are hard. So is my writing. Okay. Remember last time we do MMR, and then it was this. Right? Okay. So mu is the magnetic moment. Magnetic moment.
Moment. Okay.
The magnetic moment of the spin. right? This is NNR. Okay. For a quantum spin, we have very similar expression. Okay. So I'm just gonna use Q to represent the black vector, and I'm just gonna write this. Okay, ignoring the signs and stuff. Okay, I just want to say that from the last lecture, we see that there's a parallel. So you can define an effective B field so that this will have exactly the same form as the NR equation. Okay. So this is MV qubit. Therefore, so here, your rotation, the rotation, so let's call it B1. If you're here and your B1 is along the y-axis, no, sorry, your B1 is, your B1 is in the -1 y-axis. By this relation, you will have a force, right? You will have a force that make you move this way. When you move slightly here, you have another force that make you move this way. Is that, yeah? Yes? So the trajectory traced out by this is, according to the right-hand rule, is a circle that has its normal opposite to B1. Okay? So if B1 is along the -y, your trajectory will be opposite to B1. This is very similar to the Lenz's law, the induction of, like EMF. Okay, so you will go the other way. That is opposite to this. Okay, so just remember that. So here is the same thing. Here, for us, the effective B field, we have not drawn it, but from the rotation of this, we know that this is rotating along y, right? So this must be my effective B field minus y. Okay, so if I have a little deviation, then this should trace out. So whatever you have under the influence of the B effective field, this trajectory they trace out will be in the circle with a normal factor opposite to the B effective. Okay, that's how it works. And later, when we talk about quantum gate, I will derive a more rigorous. I will derive this more rigorously. But for now, you can just see from the parallel that this is how it's gonna work. Okay, so if you so everybody is rotating in the circle, in some circle, with a normal opposite to this, which is plus y. Okay, so this is the red is this small circle, the blue is big circle, the green is small circle. Okay. All right. Yes. Is that all? Yeah. Yeah. In the, just a side note, in the left frame, what happened is you put this, you displace this by the pi pulse, you displace this at the earlier position, and you move this to a later position because this runs slower and this runs faster. So you kind of introduce displacement to compensate for their speed difference, right? You display, you intentionally, after they run for a while, you displace this by this much, the same amount, and you displace this by the same amount. And so that at a certain moment, they will, after this much, the same amount of time, they will come together. This is like on the racing track, right? You have some runner that runs faster, some runner runs slower. Now, if you want to cheat, then you put a fast runner. You somehow like you put an on the back of the cloud, and then you put a slow runner to the front, and at some point they will all meet again. Okay. In optics, this is called dispersion compensator. Because in the pulse, this is a side note, but this is kind of fun. In the pulse, right? If you have let me just say, let me just use matter wave. So if you have an electron pulse, and the electron pulse is made of different energy states. So I'm sorry. If you have an electron pulse and a pulse has many electrons, and some electrons are generated with higher energy and some are with lower energy, right? So initially they will be like pop. Okay, I'm talking about like not one electron with superposition state, but many electrons, and each electron has its own. I'm talking about classical. Okay, so at this moment, so you have a needle, and then you kind of shine a light pulse to it to generate electrons, photoelectrons through the photoelectric effect, right? And some electrons, so they all generate at the same time, but some travel at a slightly fast speed, and some travel at a slightly slower speed. Yeah. And when as they go, this pulse will start to get broader and broader. It will spread out because the slow one will be lagging behind, and the fast one will go advance, right? So this is called dispersion. Okay, this is called dispersion. In order to compensate for this dispersion, you make it go through some kind of RF cavity, and that RF cavity will give a kick. Will give a kick to these electrons. You have some sort of phase relationship with regard to this spatial distribution of these pulses, and then it will give a kick so that the slow electrons, which is behind, it will get a kick to move faster. Will give a big kick, and the fast electron will give a kick to move slower. So that after this cavity, at some point they will come back again like this. So this is called dispersion compensator, or RF compressor or whatever. Okay, so this idea of applying some kind of inverting, some kind of compensating element to your pulse so that they can come back together. This is pretty general. This idea is pretty general. Okay, so just want to bring this to your attention because I think it's kind of cute. All right, so this is the Hans echo. It's Hans spin echo. And we are now at 3:20, so I'm gonna give you a 5-minute break. Catch some breath and drink water. And when we come back, I will show you some real experimental data of this echo, spin echoes, and you will see why it's called echo. All right?
usually pay
Oh, right, your question. Yes, yes. That's another layer of a complexion. That's another layer of complexion. That's something to do with the coherence. It has something to do with the coherence. And yeah, um, let me first see if I can find my laser pointer. Oh, of course not. Where is it? And this. And this. Oh, here. Good. I should have it here. Oh man, such a big box. All right. Good. Yay. It works. Good. Very good. Please remind me again that problem because when I talk about the coherence, I want to address the question you ask, but I may forget. So please remind me. And I finally get to use this baby. Very nice. This is a digital laser pointer. It's better, I think. I like it. All right. I don't get to use this very much. It's very expensive. I never get to use it. It's so expensive. And the only presentation I get to use it, it kind of had technical difficulties. In the middle of the presentation, I just have to leave it. Okay, one more minute. See, I can point with my head, with my hands in my back. I can do the pointing with my hands in my back. Isn't that nice?
How does it work?
I mean, it's just a remote that control the mouse.
Oh.
And when you press, the mouse become like a laser spot. Okay, so it's basically just like a mouse. It's basically just a mouse, a wireless mouse. And
But it's not incorrect.
I try to buy something, and
I
it's
want
all.
to go to a jazz concert with Japan's best jazz musician,
Uh huh.
but they won't let me.
Why? Because they don't accept your credit card.
Yeah.
All right. All right. Maybe you have to pause that for a little bit because we're gonna continue. All right. So if you pay attention, if you notice in the spin lab, we have this little thing sitting by the window. Okay. This is another teaching thing that we are supposed to use in modern physics lab, but it hasn't been employed. We're testing it. But anyway, this is an MNR device. It has this big coils outside to produce the static field, and inside this hollow tube, it has a mount that will accept like a tube with filled with liquid or some liquid or water. And then you also have in the perpendicular direction. So I guess I don't know how I never opened it actually, but some other student did, and in the direction perpendicular to this static field, there is this pickup coil, which is also uh, uh, a microwave generating coil. So it's both. It's like it serves two purposes. It generates microwave and it also pick up the the induced voltage from the rotating nuclear spin. Okay. All right. So this is what happened when you apply. So this is the signal. This is the signal in this direction. So when you have when this is the Z, right? So you need to see the. Can you see my imaginary static field and my imaginary nuclear spin? All right. So um, when when the when you apply a pulse, B field, microwave pulse, in the perpendicular direction, you flip it to this horizontal direction, right? And then here you will do free precessions, right? So if your pickup coil is like this, you will only pick up components along the solenoid axis, yeah. So when you have a lot of projection, you have a lot of field going through you have a lot of flux going through this pickup coil. When you rotate to this position, you have zero flux, right? And when you rotate to this position, you have negative flux. So the flux through this solenoid pickup coil changes, and that change will induce a change in magnetic flux, induce a voltage on the coil loops, and that's the signal you see here. Okay. Now there are a lot of so when you apply, so this it does not show. Okay. So the signal and the envelope, they are the same thing. Okay, this is just this is like a computer generate. Anyway, this is the same thing, but they're supposed to be like a really short pulse that kick it. So you start to have the signal, and then afterwards, the spin just freely evolved in the field. Okay, the spin just freely evolved in the field like this until some long time later it's thermalized, and then you'll do this. You'll do this or do this. Okay. Now, what you see here is that you see this if it start to, instead of so what should have happened if you have only one nuclear spin, right? You kick it, and then you should just stay there forever until it's thermalized, right? You should just stay in the same magnitude, like a sine wave, like a sine, yeah, just like a sine function. It will, you kick it, and then you should just oscillate continuously. This is a real-time signal, okay? And that is free precession, right? But because you have many nuclear spins with local, with a field gradient through them, so they all precessed at different speed. So you can imagine you have some wave, you have some signal that looks like this, some signal that looks a little shorter, some signal that looks a lot slower, right? When you combine all these signals together, so these are all voltage signals, right? When you combine them together, it's like you combine many sine waves together. They become, they diminish each other because they are not aligned, right? They are out of sync. So they diminish each other, so your signal goes like, goes down. This is dephasing, about 15 millisecond time. This is dephasing, yeah? Oh, crap. And then it kind of does this. So if you don't apply the second field, it kind of does this. If you just let it freely precess, at some point, they will come back again. That's called the beat, 1 over the beat frequency. You get it? Right? When you're in the elementary primary school, have you ever done a math problem? You have like 3 runners, 1 runs at a faster speed, and so the first and the third runner have run at a faster and slower speed compared to the second runner, and they all run, right? And the question is how long, how many loops, or not loops, but like how much time later they'll come back again. Okay, so there's this problem I did in primary school. So this is the same thing. Okay, so they are, yes, they are out of sync, but they won't stay like this forever. After some time, they will meet again at an instant. All these waves will meet again in phase, and at that instant there will be a peak. So this peak and wobble 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 peak, not this, is peak wobble 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 peak wobble wobble wobble. This is a typical beat pattern. Okay, when you have many frequencies in your signal, this is what's gonna happen. Okay, so this wobble that you see is that wobble 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 wobble. Now, and the beat time, so the period when this thing come back again, that is 1 over the beat frequency, and the beat frequency is the total spread of your resonance. Okay, so that's typically long time ago, long time later. So we don't have that much time. So we want them to come back together earlier. So we apply. So after waiting for some time, about 1, 2, 3, almost 200 milliseconds later, we apply another pipe pulse. This pipe pulse rotate all the spins 180 degrees with respect to y-axis, and they continue to evolve. But then, like I said, in the left frame, we put the fast runner back and the first slow runner in the front, right? And they continue to evolve. The slow runner still evolve at a slow speed. The fast runner still evolve at a fast speed. But because of this artificial displacement, they will come back together at some point, and that this is where they come back together. Okay, and as they come back together, sure enough, they will fall apart afterwards. Okay, so this is Ham's echo, and why this is called spin echo? Spin, of course, it's spin. Why it's called echo? Because when you shout to the mountain, you will hear a reflection with exactly the same sound, a replicate of your original sound, right? So this is like here up to this point, this is like the replicate of your original signal, a replicate after like an equal distance. This is like the mountain, and this is this is the equal distance, and so that's like an echo. Okay, that's why it has this name. You can also call it dispersion compensator. I wouldn't mind because that's what it is. All right. All right. So this is NMR signal. This is real signal, real signal, experiment signal, and this is I've done some simulation. I just want to show you this is how it actually works. And in this simulation, I can add in the dephasing effect and the coherence effect, so you can compare that to your experiment and see like what's going on. All right, so this is a single MV. I have only one MV, and then I have this pulse, right? And this pulse give me invert my population from 0 to 1. Yeah. And this is ensemble. So if I have many of them, right? If I have many of them, then if I have MV1, MV2, MV3, MV4, the combined effect will deviate from the single MV result in the population. And also the coherence will look different. With the single MV, after the pi pulse, you are supposed to be in the south pole, right? So there's no component in the XY plane, right? This is the component in the XY plane. There's supposed to be no component. It's supposed to be 0. And but with many of them, you have this remnant signal from the XY plane. This is Ramsey. This is Ramsey on resonance. So the first pulse bring the MV to the XY plane. The second pulse bring it to the south pole. So this is equivalent to a pi pulse. This is pi over 2. This is pi over 2, right? You do 2 step, and you still do like a pi rotation. Okay. This is the ensemble, and from this you can see clearly the dephasing effect. When you put the first one on the XY plane, you also put the second and third one and fourth one on the XY plane, right? So everybody's like around here, XY plane. Everybody's around. So the ensemble sun is around still 0. So because everybody has the same value, so the sun is still around 0.5. But now you can see there's a big change here compared to the single one, right? The single one, just like I said, you kick it to the XY plane and you're supposed to stay there for rotation. So it's supposed to be like fixed amplitude and then just go like this until the next pulse come. But now, because there are many of them and they're all oscillating at different frequency, they kind of just destroy. They interfere with, not really interfere. It is just the signal, not the physical process. Okay, they individually they are independent, but the signal, since the signal is a sine wave, you have different sine waves oscillating at different frequencies. So the signal will add, and then they will make a constant amplitude signal drop to a small signal, and then it will wobble until some point it will come back. Okay? Yeah. And why?
What is the graph frequency?
What is the, so this is just take this as u or v. This is your u and v component, and this is your w component. Okay, and this is an ensemble sum. So you have MV1 like this, MV2 is like this, but slightly different frequency, slightly different position, and then MV3 is like this, slightly different frequency, slightly different position, and you sum all of them and do an average. Okay, and you have this. Okay, and then so when you apply the second pulse, everything gets screwed up. Everything gets screwed up. Sorry. The first one, it will do this, but the second one, because it is supposed to be in a certain position in order to rotate to the south pole, right? But the MV2, because it's rotating slower, right? So when it's not there yet, but then it comes the second pulse, so it doesn't bring it to the south pole. And so this goes the same with other MV centers. So at the end, when you superimpose these signals, they become like this, and this is not this high. This is a reduced value. Okay. So because everybody's doing different things. If you apply a hum sequence, so with the pi pulse in the middle, then you can correct for this dephasing, right? So you could make them focus again. So it looks like your coherence gains you gain back your coherence, almost like that, from your signal, from the point of view of your signal. You almost get back the coherence, and then when they are aligned, and you apply the second pulse, and all of them will have the same result. But this time it is 0, because the pi poles flip it to the other side. So all of them will go back to the north pole. But now here you don't have you have like the full effect. This will be the effect as a single. This will be some very similar to a single. If you apply a Ham spin sequence, as if apply a Ham spin echo sequence to a single MV center, right? For single MV center, you first apply a pi over 2, and you apply a pi, and then you apply a pi over 2, right? It brings it back to its original position. So the ensemble and the single spin trace are very similar. I mean, so not as trace, the result are very similar. You can see here that this doesn't go up here. It should, I mean, if it is a single MV, it should go up and then down. That's the trajectory. But here, of course, because of the ensemble, you don't see that peak. But the end result is still the same. So Ham spin echo kind of correct for give you the same end result, even though your process might still be different. Okay. But now I want to talk about limitations of Ham spin echo. So it is not so wonderful as everybody think. So it is not a solution to all dephasing problems. It has certain limitations. Okay, so here I wrote volatility range. So, but I should have write limitation. Limitation. And I'm gonna do that by just show you. If you have a strong field inhomogeneity, a strong gradient, that means the field here and the field here are very different. If you have a strong gradient, that means the field in two places are very different. If you have a small gradient, that means the field here are almost the same as the field here, just slightly difference. Okay, so this is for, so if you have a small field gradients, then you have a small spread of resonance frequency of NV, correct? So this is for small spread. If I increase the spread to median, if I increase my field gradient, you can see that this becomes shorter, right? And wobble, wobble, wobble. That it kind of still work. You kind of just flip it, right? Echo. So this is like a mirror image of that. So like an echo. So for small median spread, it still work. This is slightly bigger median spread. This part is not identical. Oh, I should sorry, I forgot I have this. This part is not identical to this, but the end is almost the same. Almost the same. But if I keep increasing the spread to a large spread, so sorry, this is a typo. I should have written large spread. If I continue to increase my gradients, you can see that this side is completely different from this side. And what's more is here you have like a large value at the center of the pulse. Here you have a small value at the center of the pulse, right? So you can see that it is not echo at all. The echo is so blurred out. And the reason for that is because for different, so I'm just going to use a single, so this is a Bloch sphere, okay? For MV1, unresonant, a pulse can bring you to, a pi pulse will bring you to the south pole, right? And this will also apply for the pi over 2. So I'm using pi pulse as an example. When you have off resonance, slightly off resonant, it brings you to a different position as we draw there. It brings you to a different position. And then you start to process. So the initial position is not even here. It's there. And then, but it will still bring you back to the south pole, approximately. But when you start to, when the resonant frequency deviate even more, right? Then the pi pulse will not be able to bring you to the south pole. Even here, when you deviate a lot, right? You can see that it is not south pole at all. As you can see from the z coordinate. This is the z coordinate, right? You can see this is not this is not 0 anymore. Okay. Okay, so this is Hahn echo for one spin. So one spin is it is supposed to bring it back to the full circle, right? Because pi over 2 pi over 2 total is 2 pi. So you should bring it back to our original position. Okay, so that's the red. But if you have deviation, so that was like Hahn echo for spin 1, for sorry MV1, and this is Hahn echo for MV2. Okay, MV2 have slight deviation from MV1 in terms of resonance. So, but it will be bring back to the north pole, no problem. But when the deviation start to increase, when the resonance spread become larger and larger, MV3, you see that this is well, this is still working. It's not too bad. Oh, but for MV4, no, there are some deviations. This is past the north pole on this side. And you can see also from the z coordinate, it is deviating from 0. or when you have a lot of displacement. So the pi over 2 is supposed to bring it here, right? But anyway, overall, after this whole thing, it is not at the south North Pole at all. It is way past it. So uh, you see this spin echo technique can only be applied when your resonance spread is small. When your resonance spread is large, first of all, your first pi over 2 poles will not bring all of them to the equator, right? Some of them will be like here. Some of them are here in the equator, but some of them will be like slightly higher. Okay, that's the first one, and the second one is anyway the full sequence just will not bring this to the position it's supposed to be when the resonance spread is when the resonance deviation is large enough. Okay, so that's limitation number one. Limitation number two is you must have a good phase coherence. It's not coherence, sorry, phase correlation between the pulses. So that means the oscillation here needs to continue through the three pulses. The initial phase of this pulse needs to match with the with this pulse as if this is continued. Okay, so typically what we do is we just turn on a carrier signal and then we use an envelope to modulate it. However, if the carrier kind of drift after some time, right? Because if this spreading is too big, you can have phase noise or phase jump or whatever. It is not stable. If it is not stable for if your carrier source is not stable for like this much time, they will not have the correct phase relationship with each other, and the hand-spin echo will not work. Yeah. Remember in the Ramsey previously in the Ramsey lecture when we talked about Ramsey interferometry, I told you that the device that we have, the spin flex device we have, they produce the two poles in such a way that they just turn on and off, both the carrier and the envelope, and restart it, turn on and off. So it always start at 0, right? The carrier wave always start at 0, and then will go up with the envelope, and then when you terminate, it's shut off, and when the second one is turned on again, it will start at 0 again. Okay, so no matter how far you spread it, this spreading, the separation between the two pulses does not reflect on the initial phase of the second pulse. Remember I said that? And that is enough to destroy, that is enough to defeat the purpose of the two Ramsey pulses. Okay, you will not see fringes if you have that. Same thing here. This is basically Ramsey pulses with something in the middle. So if the phase relation cannot be maintained through all of them, this will not work. And let me just give you an extreme example of three pulses all start at the same initial phase, just like what we have with the spin flex setup. Sorry, the other way. All right, so this is Helm's echo. Okay, so this is a lap frame. This is the lap frame, and previously the block sphere was in the rotating frame, so you don't see this free precession. Here you see the free precession. This is if you first were brought. This is your block vector. The red is your block vector, and the blue is your effective B field. Okay, and first you're brought to the equator, and then you free process there for a while. That's why this you have like many. You have that's why you have many like a very thick cluster of trajectory here, and then there is this flipping pulse, and the flipping pulse will have this effect that the x it bring the xy component to 0, which means it bring the spin down to the south pole, like you can see here, right? It bring the spin down to south pole and then back. Okay, so by doing this, it flip its direction, and then it continue to free process at the equator, and then the second pi over 2 pulse will bring it to the south pole. Okay, so this is um, so this is single. Wait. I want to show you this. So this position marked by blue here, this is before the pi pulse. So this is your spin position. And after you apply your spin, pi over 2 pulse, you see it rotate to the mirror position with respect to the effective B field. Okay, so that's what I want to show you here. All right, so this is if you remove the phase correlation. So this is all single MV, okay? But if you remove the phase correlation between the pulses so that they always start with the same initial condition, then the effect is, okay, again, before the pulse, I have it here, I mark it here, but then after the pulse, it doesn't flip to the other side. You see? It doesn't flip to the other side. It does not, this pi pulse is not doing what it's supposed to do. So it's very important to have that phase correlation. And I can explain it, but I don't want to. It's just too much trouble. All right. So, okay, that's limitation number 2, phase correlation. So we need to have a small phase gradient or in small field inhomogeneity and phase correlation between pulses. The third one is I want to talk about spectrum. So this is a single MV spectrum, right? And this is also a single MV spectrum, but for a different MV. Do you see the difference? I know the figure, the size is different, so it appears different. But focus on these marks. Do you see there's a dip? So align with 1, so this is on resonance. There's a peak, right? But here, align with 1 is there's almost a dip, right? So if you all right, and this is the coherence effect. So if I have only 1 and I have the coherence, it reduces its visibility. If I have no decoherence and I have just the ensemble, it does very similar things. It reduces the visibility, right? So the question is, can I use Hahn spin echo to correct for this? If there's no, suppose my coherence is good and my spectrum just got messed up by the phasing effect. Can I use Hahn spin echo to fix this problem? So that I can get back to this very, very nice contrast of single MV spectrum, Ramsey spectrum. That's the question. We cannot do anything about decoherence, but can we use spin echo to correct for this spectrum? Okay, this is dephasing and decoherence together. This is worse. All right. This is Hahn spectrum. So for a single spin, for a single MV, it is supposed to look like this. Also, this looks a little different from the Ramsey because at resonance you have 0 instead of 1. The rest is almost similar. Yeah. So compare this to this. This is like if you put the top one, the center one, if you brought this to 0 and keep the other ones untouched, it's like the Ham cycle. Okay. So now the question is, so if I have a single spin Ham echo, so a single MV Ham echo is similar to a Ramsey a Ham spectrum is similar to a Ramsey spectrum. They both have fringes. It is just they have a slightly different overall shape, but that's fine. The question is, when, of course, when for different, as in the Ramsey, as for the Ramsey spectrum, when you have a different MV with slightly different resonance frequency, your Ham spectrum shift position, right? So that when you put them together, the peak and the dip will match, and then they will reduce the they will not reduce the like this part is mostly fine. It is still close to 0. This is a coarse feature, but the fine fringes, those are the fine features, and the fine feature gets screwed up very easily by this displacement, right? So you can see all of them when they sum, when you do an incoherent sum, the fringe visibility is like reduced to almost 0. If you have not a ensemble dephasing effect, but you have, like strict decoherence, and you're looking at single, what it does is it will bring this up, so that you see that this knot here is actually an interference effect. That's very interesting, right? It is an interference effect, and that interference effect is a very gross feature, so it's not harmed by the dephasing too much, but the fine feature of the interference effect get kind of destroyed by the dephasing. But here you see that the visibility is reduced, but you can still see some good peaks here and there, right? But if you have both ensemble, you have both ensemble dephasing, and decoherence, then you have no dip in the middle, and then you have no fringes at the sides. Okay. Do I have an example of? Oh, I'm sorry. Oh, crap. Damn. Okay, this is so annoying. Oh, yeah, that was my point. Sorry, I forgot. Dephasing, right? So supposedly using a Ham echo, you can fix the dephasing problem. That was my point. Yes, sorry. My point was, yeah, you have, like, from the idea of correcting for dephasing, right? It sounds like the Ham spin echo can undo dephasing effect, at least for the trace, right? But for the spectrum, as far as the spectrum goes, the question is, the Ramsey spectrum gets screwed up by the ensemble dephasing. Can we restore it by the Ham spin echo, right? So the question is, does the single MV Ham spectrum and the ensemble Ham spectrum, are they similar? That was the question. And here we see that they are not similar. The fringe, they are similar here, but this is not affected anyway. These fringes they are gone. They are still gone. just like in the Ramsey spectrum. I hope you get the point I'm trying to say. So Ham spin echo cannot be applied to fully undo the ensemble defacing effect. It can only be, it's only useful in certain application, like when you care about the chase, you can do that. Okay, but if you care about the trace of, like something, you can do that. But if you're doing like spectroscopy, you cannot do it. It's useless. Here is from our teaching lab. This is the real data. So this is a Ramsey. This is a Ramsey spectrum. Okay. And here's the Ham spectrum. Okay. Tell me, what do you see here? Like, what feature do you see here? Do you think the coherence is at work here? Do you think the phasing is at work here? Like, what do you think? What do you see? Earlier, I have add the phasing and the coherence separately, and I've also add all of them together. So you know like what each effect does to the spectrum, right? So now we are using the spectrum to probe the quantum coherence and the quantum ensemble dephasing. And this is real data. And I don't, of course, this is not a simulation, so I don't know how much dephasing we have, how much the coherence we have, I don't know. But from the feature of the spectrum, what do you think? What is at work? Do we have dephasing? Oh, sorry. Or should I ask, do we have the coherence? I mean, I should make this a quiz, but there's no board. I cannot put yes and no. If you think there is the coherence, remain seated, and if you don't, oh sorry, if you think there's the coherence, stand up.
Decoherence.
Yes, the coherence. Just stand up. I will not make you debate with each other. I just want to see what you think. Okay, everybody stand up. It's so hard to get everybody to stand up. If you think there is the coherence, sit down. If you think there is the coherence here, sit down. Okay? If you think there is, I mean, from here, it's really hard to tell whether there is the phasing or the coherence. Like, it's really hard to tell this apart, right? Because they all produce the same feature. They just diminish the visibility, right? But Ham echo has more features, so you should be able to see if the phasing and the coherence are at work here. If you think there is the coherence at work, if you think the coherence at work here, sit down. So we have 2 vote for decoherence, yes, decoherence, and 4 vote for no decoherence. Yep, good. Stand up, please. Now, next question. If you think there's dephasing, ensemble dephasing at work here, sit down. Okay, interesting. We have people who think, so we have people who think they are both dephasing and decoherence. We have people who think there's only decoherence. We have people who think there's no decoherence and no dephasing. Wonderful. We have like a very wide spread, a wide distribution. Sit down, please. Thank you very much. Okay, first of all, if there is no decoherence or dephasing, we should have full visibility. That means this thing should go down to 0. This should go down to 0. This should go down to 0. This should go down to 0. all the dip should go down to 0, right? That is when we don't have any dephasing or decoherence. Obviously, that's not the case. Okay, so that's something to remember. Now, question is, oh crap. Question is this diminished of fringe visibility due to decoherence or dephasing or both? Personally, I think it is due to decoherence because I see that this get lifted up, right? I mean, dephasing cannot lift this up because this is a it has a this dip has a very wide width, so a little displacement wouldn't hurt. So this is not a sensitive feature, a dephasing sensitive feature. The fringes are, but this is not. Okay. So dephasing cannot do this. That's what I want to say. The bottom line is dephasing cannot do this. Only decoherence can lift this up. Okay, and the tau pulse is 400, 420. 420 means this and this are apart from each other 420, and this is 210. Okay. All right. So that means, like this tells us at least at 420 nanoseconds, I have already a certain amount lost of coherence. Can there be dephasing? Also, not so sure. It's hard to say from here. But there's another experiment I did, and this is totally cool. I like it. If there's dephasing effect, if there's no dephasing, it's only decoherence, then as you spread this time delay further and further, right? What do you expect? Your fringe visibility will go lower and lower and lower and lower until you have nothing, until you see the Ramsey basically. Okay. But if there's dephasing, if there is ensemble dephasing, as you increase your post separation, your peak become finer and finer, right? So the same amount of displacement for one configuration could be this. For the other configuration could be this. You see what I'm saying? So the same amount of displacement for one configuration, for one fringe size, or for one fringe width, it could means, cancellation. But for a smaller fringe width, it could mean alignment. So as you change your post separation, you can see a visibility revival if dephasing is at work. So from the hum data, it's really hard to say, and we know there's for certain is decoherence, but we don't know if there's any dephasing. I mean, it would be reasonable to have dephasing, but it's hard to tell from the fringes because both dephasing and decoherence diminish the fringe visibility, right? However, from another experiment, we can see if there's visibility revival. That is from Ramsey. So this is Ramsey. At low separation, I have fringes. As I separate them further and further, my fringe goes disappear. But then, as I continue to separate the two fringes. They come back again. The fringe come back again. Fringe revival. So this means I have dephasing also at work during this period, during this time. I mean, dephasing is always at work. So I have a constant dephasing here. But now when I separate this further and further, you see there's no fringes anymore. And that's because of decoherence. Decoherence eventually will kill all fringes for individual MV, not to say the ensemble signal. Okay? So I think this is kind of cool. I want to share with you. And this is the full, so this is only up to 650. And I have done this up to like 2000. And you can see the hem, this is the hem fringe, right? You can see fringes, and this here, like up to 1000, it doesn't, it kind of, it's not clear that we still have it. But here we have it. Within 1000, we have it. But this give us a even better, right? So we have fringe revival for this much time. So if this will be a fully coherent, we should have again and again and again. Of course, the time will not be the same, but we should have repeated fringe revivals. This diminishing and revival, diminishing and revival. But then here we don't have fringe anymore, and they continue to cease to exist. So we can tell from the Ramsey spectrum that after 600, we basically have zero coherence left for individual MV. And that is kind of in agreement with the ham, except that ham here, it's harder to say because you still have some kind of structure, so it's harder to say. But from the Ramsey, it is very clear. Okay, so 600. So basically, from this, you know your decoherence time is 600 nanoseconds. And this is important. This number is important because any quantum gate you want to apply to this qubit has to be done within 600 nanoseconds. And you know how much your pi pulse time is, right? It's usually around 100, right? So how many gate can you fit in? 600, maybe 6 at most, right? Then otherwise you have to apply a very strong drive, that will probably be able to shorten that pi pulse time. But anyway, that's other things. So okay, so this is nothing. Okay, cool, good. That's all I want to tell you. And so that's all for Ham spin echo. The purpose of this lecture is to introduce you the Ham spin echo and its working principle, and tell you its limitation. It is not as magical as a lot of people think. It has the limitations. Okay. Okay, cool. Quiz time.
So the significance of tau.
Oh,
is to just make
thank
sure
you.
everything
Yeah.
happens before it decoherence.
Right.
Okay.
Yes.
But it doesn't really matter how far apart each pulse is. I mean, of course, the signal is gonna.
The fringe size the fringe width will reduce.
With longer tau.
Right. It will become finer and finer with longer tau. The dephasing is always there. I mean, it is fixed. You're given a fixed set of ensembles, so your resonance, the distribution in your resonance frequency is there, regardless of how far you put your pulses apart. What would matter is the only fact this tau will do is whether it is within coherence time or outside of coherence time. If it is within coherence time, then yes, it can do a lot of things. But when it is outside, then all the gates, this will be invalidated. They will no longer be valid. Okay, so if this is 10 and this is already 600 nanoseconds, these basically are useless. They're not doing what they're supposed to do. They are not like doing this in sequence. They kind of, they are, yeah. I mean, there's no coherence. What can you do with a spin with zero coherence? Yeah, a quantum spin with zero coherence. Okay, so yeah, I just want to say that a lot of people use Hahn spin echo to characterize, even people who do research on MV centers. A lot of people use Hahn spin echo to characterize the coherence time of MV qubit, and they claim that the coherence time is like super long, incredibly long, because they are using the trace. They're not using the spectrum. Yeah, and you know the trace will always work, right? What I'm trying to say is, I guess my point is the coherence time of MV qubit is not as long as people like to believe. Yeah? Good. Great. Awesome. But it is still wonderful. I like it. You don't have to go through the pain of clean vacuums and low temperatures and all that stuff. Yeah? You know what I'm talking about. Oh, yeah, I know it's painful. I've played with that too. Okay, quiz. All right. So let's see. Quiz number 1. Does Hahn echo only work for resonant or near resonant excitation? Not or, and near resonant excitation. Okay? Second question is, can the pulses in a Hahn echo start with the same initial phase? Okay, great. Okay, yes and no. Yes and no. Okay, stand up, please. And then for question 1, does Hahn echo only work for resonant or near resonant excitation? Yes, if you think it's yes, stand on this aisle. No, stand on that aisle. So we have Clement say no, and the rest say yes, correct? Okay, I like that. You know, I always like people to have different opinion because they might be right. Yeah. So yeah, why don't you, Clement? Why don't you try to convince Marlene because she's very hard to convince. Why don't you try to convince Marlene and everybody can just listen? Why don't you try to convince Marlene why it should be no?
I'm just guessing. I don't know.
Well, you have to have some reason to guess that, right? And there must be a reason on the back of your mind that will lead you to this answer. What's it? Please.
There really isn't.
There really isn't.
Yeah, there
Great.
really
You just want to be different.
No, I just don't know what to choose.
Marlene, then could you tell that tell Clement that he is standing at the wrong spot. He's standing on the wrong aisle. He should be joining you.
No, I can't either.
You cannot either.
No.
Man. Oh. If I would put a third aisle, say I don't know, I have no idea. I guess probably everybody would just stand there. All right. How about you, Mark? You're second in line. Can you convince? Can you tell Clement why he is wrong? You need to look at him.
I'm not sure.
Do you think you shift position will? Hey man, it doesn't matter. I remember your position.
I'm not sure.
What?
But when we do it, we set a frequency.
Of course, you set a frequency.
Uh,
You didn't have this lecture before you did the experiment. Now you have this lecture. So I hope you have a better understanding of what you're doing. Does ham echo only work for resonant or ending and resonant excitation? I just feel like I need to write this better. Start staring at me. This is your show. Oh, I'm done. Okay. All right. Mark gave up. Ask Marlon. How about you, Han? You're the third in line. You're the third in line for the throne.
I'm not quite sure what this question means, but my understanding is my understanding of the question when you do
Speak louder.
when you do like this, you have this one we call resonance frequency.
Okay.
I think the question is say you can only do near this and not this.
No, I'm sorry. The question is not about the spectrum.
Okay.
The echo effect. Okay, remember what's the echo effect? The echo effect is in the trace, right? The reason I show you the spectrum is to show you that it doesn't work for the spectrum. Okay? But for the trace, it does work, right? So I'm asking you, does the hum echo trace? Okay? So the correction of the phasing in the trace, that's the hum echo. Does that only work for resonant or near resonant excitation?
This one where it works if this is large.
Yes.
Oh.
Yeah, that echo. Remember? You see like almost like a mirror image after the pi pulse, a mirror image of the same thing before the pi pulse. It's like an echoing, it's like a reflection.
Yeah, I think it works for even it as near resonant means this is small.
Yes.
Oh, then I think it doesn't. I change my answer.
You change your answer. What's your answer?
Graphs you show us, right? It's like the low offset and medium offset and the large offset.
Yeah.
And then we see like the signal. Does it like inverse?
Right. For a small spread, you see a perfectly inversed signal. That's like the echo effect. But this reflection, this replicate, deteriorate, or it lost its fidelity when the spread is larger, becomes larger and larger, right? All right. I think you cannot take it anymore. He needs to speak up. Yeah. Yo or you? Yo, yeah, yo, yeah.
I think if you are fine tuned and the state vector in Russian field will not point at the pole.
Uh huh.
Okay. So I think it's not. It didn't work.
Uh huh.
It don't work.
Okay. You hear that, Clement? Do you hear that? Do you hear his argument?
Yeah. When it's too far away from resonant frequency, it wouldn't spin the vector at the right part of the block space, right?
He said that he. Could you repeat what you said? Yo.
If you're far tuned, the state vector will not return to the pole again. Okay.
That's what he said. I'm not trying to convince you. I just want to make sure you hear what he said. Okay. So that's Yo's answer. What about you, She?
Yeah, I think the same. It will not be not come back to the pole again when you give it time echo experiment.
It will not come back to the pole again.
Yeah.
Okay. So Clement and everybody, this is the second round. Reshuffle. Do you want to change your position? If you want to change your position, move now. Okay. After you hear what they say, if you want to stay in yes, stay here. If you want to stay in no, stay no. But if you want to change your position, you can do it now. He's still struggling. Cannot decide. All right, so I guess you are staying there. Okay, cool. Okay, very good. Okay, the answer is yes. Yes. And the answer is exactly as they said. When you are 42, all the pi over 2 and the pi and they all work. They don't work the same way they are supposed to work for resonant one. The effect, you don't even the first pulse will not bring it to the equator, and the second one will not like flip it if they are far detuned, if they're very far from the resonance. Okay, cool, good. So the spin echo, of course, this construction will not work. Yeah, because each pulse is not supposed to do what they are supposed to do, right? Second question is, can the pulse in a ham echo start with the same initial phase? Okay, choose your answer. Everybody know what this means, right? You have 3 microwave pulses, and they have certain initial phase. Can that initial phase be the same for all 3 of them? Like, for example, 0? Can the initial phase be 0? Yeah? What do you think? It seems like you are still like stuck with the previous question and you're just not moving. Are you choosing no for the second?
Yeah, I'm choosing no for the second.
All right. Okay. Cool. All right. Yes. Yes. The answer is no. Correct. Yeah. We have actually have emphasized this point for several times already. Okay. Cool. So it looks like this message gets into your head, and that's great. All right. Thank you very much. Let's get to work in the lab.